Hi team, we are ready for 4.3, one-to-one and inverse functions. Well, let's first define what a one-to-one function is. Not only is every input mapped to only one output, that makes it a function. So it has to be a function first, but then every output is also mapped to only one input. Okay, so it's a monogamous relationship. So you may recognize these three graphs. We talked about these three when we're looking at a function. This first graph is definitely a function. Every x value is mapped to only one y value. But if I picked a y value, say like 2, notice it has 3 different x values mapped to that one y value. So if we were to pass a horizontal line through that graph, it would hit the graph at more than one point. So this guy is a function, but not one-to-one. Our second graph is a line. And again, this line, this linear equation here was a function. Every input x had only one output y. But you would also notice that if I were to pick any y value, let's say -2, it is mapped to only one x value. So if we were to pass a horizontal line through this graph, it would hit the graph at one point at a time. So not only is this a function, but this is a one-to-one function. Our third graph, the circle, if you remember, is not a function at all, because if I were to pick an x, let's say 1, it hits the y twice. So it has to be a function first before we check to see if it's a one-to-one function. So we don't even need to check here. But it wouldn't pass a vertical line test nor a horizontal line test. So this guy is just not a function at all. So again, vertical line tests if it is a function. Okay, got to do that guy first. A horizontal line tests if it is a one-to-one function. Okay, but again, it must pass the vertical line test first. Has to be a function first. Now, if graphs are one-to-one, we can look at their composition of each other. Let's say we had two functions, f of g, f and g. If we took f of g and got x back, and then reversed it and took g of f and got x back, then f and g are said to be inverse functions. Now, a quick recall, remember the composition of functions means if we had f and we plugged in the g function into it, and then if we had the g function and plugged in f into that. So you have to do it both ways and get x back, or your input variable, whatever it is, every single time. So just like we have inverse operations, addition, subtraction, multiplication, and division, we also have inverse functions. The notation for an inverse function is f with a -1, looks like an exponent up here, superscript of x. Do not confuse it with reciprocal, okay? So you have to look at the context. If that -1 up there in the exponent position is within a function notation, then it is in fact an inverse function of the parent function of f of x. You do not flip it. One interesting thing about inverse functions, if f of x has the point, let's say AB, its inverse function will have the point BA. I love having questions like that on like a test or a graph. Let's say down here, if I said, if f of 3 equals 10, I would ask you to find one point on f inverse. Well, if this contains the point 310, then f inverse would contain the point 10.3. It's a real easy point or two on a test, but a lot of people miss it. But this is a basic foundation here. And also remember, a function must be one-to-one in order to have an inverse. So one of the things that we can do is we can restrict the domain to make the function one-to-one. In other words, say we're only going to define it from 0 to infinity to keep it a one-to-one function. Okay. And the very last piece of information is their graphs are reflected about the line y equals x. So a couple of things. This piece of information up here at the top helps us to verify if two functions are inverse functions. And this piece of information here helps us to find an inverse. And we'll do some examples down below. So our first example, we're going to be evaluating functions and inverse functions by looking at a graph. So in part A, it asks us to find g of 6. Well, notice the graph that's being given there is the g function. So they are giving us the x value, which means they're wanting us to find the y value. Well, if x is 6, that would be right here. We can move up and we find that the y value is 4. So g of 6 equals 4. That tells us we have the point 6, 4 on g. Now, if we're looking at part B, B is asking about the inverse function. Well, the inverse function isn't graphed, but remember the inverse function goes backwards. So this is like saying g inverse of y equals x. Remember how I said if one has the point AB, the other one has the point BA? So we'll read it backwards. So this time they're giving us the y value of 1. So if y is 1, then that will give us an x value of 2. So the inverse function would have the point 1, 2. In example 2, we want to determine algebraically if two functions are inverses. Well, if you recall from above, that means we have to determine if the composite function f of g equals x, as well as the composite function g of f equals x. Okay, that is what we need to find out. So let's do f of g first. So remember, we want to keep writing f of g means f with g of x being input. We replace that with the function x plus 1 over 2. And now we're actually going to put that into the f of x equation. So 2 times x minus 1. So instead of x, we're putting in the entire g of x function. So here the 2's divide out. We will be left with x plus 1 minus 1, which does in fact equal x. So every operation in there undo each other, so to speak, and we're left with just the variable by itself. So the f of g checks. Now we have to try g of f. So when we plug in f of x into g of x, we don't need the parentheses anymore. The 1's reduce, the 2's divide out, and we are left with x. So f of x and g of x are in fact inverse functions. In the next example, we'll be graphing to determine whether or not the function is one-to-one to begin with. And then if it's not, we'll need to restrict that domain to make it one-to-one so we can find its inverse. So let's first graph this equation here. Notice it's in vertex form with an a of 1, so there's no stretching or compressing. So that means that we have a vertex of 3, -1, so we can graph that over here, 3, -1. Since there's no stretch or compress, it has the same format as a standard parabola. But if you're not quite sure how that works, you can still plug in some values for x and y. If we go to the right, let's say we plug in 4 and 5. If we plug in 4 into the equation, that's going to give us a 0. So 4 is 0. So if you remember the axis of symmetry, if you have the point at 4, 0, then there's a mirror image just on the other side of that axis of symmetry. If we plugged in a 5 into the function up above, that would give us a 2 squared, which is 4. 4 minus 1 would give us a 3. So we have the 0.53 and another point across here on the mirror image. So this is what the graph would look like. Now, even though this is a function, it is not one-to-one. We can tell because if we were to pass a horizontal line through that graph, it hits the graph at more than 1 point. So that means we need to restrict the domain in order to make it one-to-one. So in order to restrict this domain, we probably want to start at the vertex so we can get as much of this graph as we possibly can. So we will restrict the domain to where x is greater than or equal to 3. In interval notation, that would be 3 to infinity. So that means we would only take a look at this part here to the right. That part of the graph would be one-to-one. So if we're asked to find f inverse of x, and again, let's recall that f of x is x minus 3 quantity squared minus 1, where x is greater than or equal to 3. We've restricted the domain, so it's one-to-one. We're going to use the fact that if one function has AB, its inverse would have BA. So the first thing I want you to do is replace that f of x with a y. So we have two variables that we can work with. Now, let's switch that x and y. That gives us x equals the quantity y minus 3 squared minus 1. Now, solve for y. Keep in mind, we're wanting to get y by itself. So we're going to take the square root of both sides and then add 3 to both sides. So this actually gives us our inverse function of 3 plus the square root of x plus 1. Now they're wanting us to graph f and f inverse on the same set of axes. So again, f of x is x minus 3 quantity squared minus 1. F inverse of x, and here's where x is greater than or equal to 3, where the inverse of x we found to be 3 plus the square root of x plus 1. Now, as you recall, we restricted the domain for f of x, which means the domain for f inverse will probably be restricted as well. Well, if you remember how to find the domain of a square root, we know that that x plus 1 has to be 0 or larger. In other words, it has to be positive. So just by the nature of this function, we know that this x value has to be greater than or equal to -1. We put in -2, then we're taking the square root of a negative number, and we're only dealing with the real number system, so we can't do that. So one of the things I want you guys to note, just as if f of x has the point AB, the inverse has BA, that also works for their domain and range. So for example, let's go ahead and graph f of x again. But on that restricted domain, remember it's that right side of the parabola. So we had a vertex at 3, -1, and a point at 4, 0, and at 5, 3. Okay, so that's f of x. So for f, it had a domain where x was greater than or equal to 3, that it also had a range. Notice the y values start at -1 and go to infinity. So the range is y has to be greater than or equal to -1. So guess what? When we look at the inverse, okay, that inverse function, its domain is x is greater than or equal to -1. So guess where our range is going to start? Everything flips, right? So our range value of y is going to be greater than or equal to 3. Kind of cool, right? Let's choose some values for the F inverse. We've already graphed F. So if we have X values and F inverse values, remember if one has the point AB, the other one has the point BA. And also I want that square root to come out to be a nice perfect square. So let's choose some numbers wisely. For example, let's plug in a -1 in for this X up here. -1 and 1 gives us 0. So we get the point -1,3. Yay. If we plugged in the point 0 for X, we get the square root of 1, which is 1. So 3 plus 1 is 4. We get the 0.04. And last but not least, if we plugged in the 0.3 in for X, that would give us the square root of 4, which is 2. 3 plus 2 is 5. So we get the 0.35. All of those points are opposites of the points that we get for f of x. They're switched. So if we take a look at this graph here, and we were to graph the line, I'll just graph the line through here, of y equals x, that line just splits the first and third quadrant right in half. So notice how these two graphs are kind of mirror images of each other across that line. So that's how we can kind of take a look at the functions. Did I have to do this table to graph f inverse? No. I could have taken the entire table, all the points of the f of x function, which was 3, -1, 4, 0, 5, 3, and I could have just switched them around. But it's always nice to verify that the function that you got does in fact give you those points back. So we're going to do 3 more examples of just finding the inverse function algebraically. I think it's good to have that kind of practice. So remember, the first thing we do is we change that f of x to a y value, and then we switch. We turn all the y's into x's and all the x's into y's, and then solve for y. So we add 2 to both sides. We get x plus 2 equals 3y, divide both sides by 3, and we get the inverse function of x plus 2 divided by 3. The next example, we have the function j of x equals the square root of x minus 2. We're going to write that j of x as a y value, and then change all the y's to x's and all of the x's to y's. To undo a square root, we would square both sides. That would give us x squared equals y minus 2. When we add 2 to both sides, that will give us our inverse function of x squared plus 2. So for this one, again, we have h of x equals 2x plus 3 over x minus 1. Again, we're going to replace the h of x with a y. And then switch all the y's to x's and all of the x's to y's. So that gives us x equals the quantity 2y plus 3 over the quantity y minus 1. So we still need to solve for y, but this is where it can get tricky for some people. We're going to clear this fraction by multiplying both sides by y minus 1. We're going to distribute the x, so we get xy minus x equals the 2y plus 3. But remember, we're trying to get y by itself. So get all of the terms with y together, and then all the terms that don't have y together. So let's move the 2y to the other side. So we're going to subtract 2y from both sides. That gives us xy minus 2y minus x equals 3. So the 2y terms are on the left, but so is that x. So let's move the x. Let's move the x to the right. So we're going to add x to both sides. That gives us xy minus 2y equals x plus 3. but we're still trying to get y by itself. Okay, so get all the y terms together. And what can we do on that left-hand side to get just one y? Factor. Good. We can take out the y as a GCF, which leaves us with x minus 2 equals x plus 3. Since y is being multiplied by that binomial, we can now divide both sides by that binomial. They divide out on the left, and we get y equals x plus 3 divided by x minus 2. So that would be our H inverse, our inverse function, which would be x plus 3 over x minus 2. All right, guys, if you have any questions, don't hesitate to contact me or your instructor or go get help. That's what we're here for. Bye.